Okay, so today we're gonna finish 12.4. 12, starting with 12.4. Just two sections, so it's pretty tiny. We're probably gonna finish earlier today, I imagine. There is some details here in this section, which I don't know. So for some reason, it reminded me of lexicoscoping.
It all, everything always comes down back to scoping, doesn't it?
Well, you have a merge process that essentially merges two scopes, and you have the idea of parents. Like I've seen this before. Uh, okay, so computation spaces are an abstraction that permits the high-level programming of search abstractions and deep guard combinators. With them, the computation model looks like what we've seen before. All the search abstractions of chapters 9 and 12 are programmed using spaces. Spaces have the flexibility needed for real-world constraint problems, and they can be implemented efficiently. In real-world problems, the modular implementation using copying and recomputation is competitive in time and memory use with the traditional systems using trailing-based backtracking. Sure, I believe that. This section defines what they are, the operations that can be performed on them, and gives an example of how to use them to program search. Okay, so let's remember what are them. A search strategy defines how the search tree is explored, depth-first search or breadth-first search. A distribution strategy defines the shape and content of the search tree, how many alternatives exist at a node, and what constraint is added for each alternative. Computation spaces can be used to program search strategies and distribution strategies independent of each other. That is, any search strategy can be used together with any distribution strategy, so they are orthogonal.
Indeed.
Um, yeah, but again, it's still a mystery, even after reading this today's pages. It's still a mystery. How do you generate the deduction constraint?
Uh, well, basically, uh, keep in mind I haven't actually looked at the Mozart source code, so I'm not sure if it's exactly how it's implemented, but I have an idea. It's basically um, you need to have some kind of way to accumulate partial information, so you need some kind of mutable cell, which is not general purpose mutation because it only allows you to add more details,
It's
more
monotonic.
information. It's monotonic, yes.
Yeah, they say that
Um,
later.
and those cells, um, they need to allow for reactivity in the sense that whenever you add information to them, they need to be able to send out a signal to any propagators that might be connected to them.
Yeah, no,
And
that's fine, Marinho. But that's still not answering the question. How does a propagator generate a new constraint? Where is the
uh,
code? I want to look at the code that does that.
we're probably not gonna see that because I'm guessing this is actually buried in the runtime system because it needs to be like it needs to interact in non-trivial ways with data flow variables, right?
But that's still
Uh,
not what I'm looking for. I'm looking for the generator of deductions. That's what
well,
I'm looking for.
remember when we were implementing addition in Karuta on the WAM.
Yeah, there was a particular pattern match that would allow me to find that.
Yeah. We were basically saying, okay, if these two variables are defined, then we need to do something to the third one. And we had basically three patterns because there were three variables total, right?
Yeah,
A propagator would do basically the same thing, except
it's
it
user
would need
defined stuff, not runtime specific.
um, yeah. A propagator would need to do basically the same thing, except instead of just running once and instantiating the variable once and for all, the third one, I mean, whenever any one variable is updated with additional information, it needs to look at that one and at the other ones however much information they already have, and then um, like it would need to further constrain the other ones. For instance, if you start with like I don't know, you have a plus. Let's say we're using plus just for simplicity, okay? When you do that x plus y equal colon 10, right? That's basically a propagator that's observing three cells, x, y, and a cell that's already has the constant 10 like defined inside of it. Um, so initially, when it's called, it needs to look at the three cells and see, okay, what's already in them. It's going to see that x and y are two intervals, right? Um, and 10 is a constant. And there's nothing really it can do at this point because the intervals and the constant, they don't have enough information to refine anything with the plus by itself. But as soon as any one of the three gets updated, it needs to see, okay, x got updated. Let's say it was x, just for the sake of an example. It has been refined, so instead of being 1 to 9, it's now something like 2 to 8. Okay? It needs
That's
to look at,
fine.
okay, so it will look at x and say, okay, got updated. I know that the 10 is a constant, so it will never change. But those two things together, they let me constrain y, you see?
No, man, I completely see how we would do this ourselves. Like, the step-by-step process you're describing is completely understandable, and I would do that on paper. But it's not the same thing as understanding the complexity of implementing that in a programming language. So, for example, the example that you gave of the plus in Karuta, I would say that even if I knew how to deduce something out of the plus operation, I would not be able to have a very good, a very accurate glimpse on how would that look like in OCaml code. I would have to look at the code to see if there was any cleverness, any tricks, to see if we can optimize something that I can't, or I won't in the paper version. And that's what I think that I'm frustrated because, of course, I understand what you're saying. Oh, you have these two things and you have intervals. On a high level natural language description, everything makes sense. We are humans after all. But I'm very frustrated that there's actually no mention. Like there's like very loose drawings of rectangles and things like this, and there's no code that actually does the part of, okay, a new constraint was found. Let's now use this system to put that in. You see? Like it's a very
Yeah,
different thing. It's a very different thing than just like I said, everything you said makes sense. I cannot dispute it. It makes complete sense. But that's how I would do it naively on paper. How what does the code do?
that's a fair point. Yeah, the book doesn't really go into that level of detail, which is unfortunate, I believe.
No, it's very inconsistent because we went through a bunch of levels of detail in other systems before. This is the first time in my recent memory that we are actually making something very core to the functionality opaque. But anyway, so here's how it's done. Create the space with the correct program inside. The program defines all the variables and constraints in the space. Let the program run inside the space. Variables and propagators are created. All propagators execute until no more information can be added to the store in this manner. The space eventually reaches stability, which we're going to have to see what this means. During the space execution, the computation inside the space can decide to create a choice point. The decision which constraint to add for each alternative defines the distribution strategy. Yes, one of the space's threads will suspend when the choice point is created. When the space has become stable, execution continues outside the space to decide what to do next. There are different possibilities depending on whether or not a choice point has been created in the space. If there is none, then execution can stop and return with a solution. If there is one, then the search strategy decides which alternative to choose and commits to that alternative. Okay, and now we're going to go to the definitions. So essentially, this is the code. This is the DFE search. Um, depth first single solution search. This explores the search tree in depth first manner. And then there is a description of what the code does. And then the search function uses primitives such as new space, ask, commit, clone, and merge, which are the ones we actually going to see how it's done. So the script example. So let's use the search engine on the example given. The problem is specified a procedural rectangle. And so this is essentially the output, the solution output. Then we do this thing to define to acquire the variables, and then we do the constraints and let it fly. We start the execution by this statement, where DFS and the rectangle are defined as above, and sol is the fresh variable. If we expand the body of the function, we should create two variables, say s and l, leading to a configuration like the following. The box represents the thread that executes the statements, and below it's a representation of the store. It is a representation of the store. So this is how it looks like. So the first primitive is the space operation, which is the new space. It creates a new computation space S with a root variable root and one thread that executes a rectangle root. Both the new thread and the new store are shown inside a box which delimits the boundaries of the space. So this is the imagery, the pictorial representation of what is happening there. A precise definition of new space is this, when given a unary procedure P, creates a new computation space and returns a reference to it. In this space, a fresh variable R, called the root variable, is created in a new thread, and PR is invoked in the thread. Yeah. And then the hierarchy of spaces, which is this thing. So let's say that you have threads TA, TB, TC with the top level variable X available there. And this is the hierarchy, right? So TB has TA as its parent, and you have TC with TB as its parent. If TB binds X, then TB and TC will see the binding, which means that the children see the bindings of its direct parent. TA won't unless space B is merged into space A, which means that it's only one level of sharing things. Grandparents do not have that privilege. And this is because child spaces are speculative. They may or may not become part of the parent store. Because space C is speculative, only TC sees Y. So this means that the visibility is not bidirectional. It's only in one direction.
Yep.
Yeah, and then there is like more nomenclature. So tree structure. So we have childs, we have parents, we have ancestors and descendants. And then threads and variables belong to spaces. A thread always belongs to exactly one computation space. A variable always belongs to exactly one computation space. Now let's focus on the space S. This thread inside is runnable, so we will run it. The reduction of the procedural call rectangle root gives this new order rectangle, which apparently the rectangles represent threads. You might have
Um,
noticed that the variable rectangle is bound outside the space. Go, Mari.
they are actually, well, spaces, but spaces have threads inside of them.
Yeah, which do not prevent the inner thread to read its value and use it. Computation spaces do respect precise visibility rules. So, variable visibility. A thread sees and may access variables belonging to its space as well to all ancestor spaces. The thread cannot see the variables of descendant spaces. Figure 12.4 gives an example with bindings. Wait. I know that this makes sense. Basic constraint visibility. A thread may add basic constraints to variables visible to it. This means that it may constrain variables belonging to its space or to its ancestors. The basic constraint will only be visible in the current space and its descendants. Um, that is, a parent space does not see the binding unless the current space is merged. Yeah, so this is essentially the direction of what's being shared. Visibility is shared, but the constraints are only like one direction. Well, both are only one direction, but it's opposite directions.
Yeah.
The thread inside the space continues execution, creates two new variables x and y inside the space, and binds this. This gives this. It then tells the basic constraints to the constraint store of the space and create new propagators, each one on its own thread. Yeah, so essentially this turns into that. Concurrent propagation. Now new propagators enter the scene. As we've seen the section before, they propagate concurrently, reducing the domains to 4, 6. Yeah. So this is where it's opaque. They just come in. They just say hello, welcome, we're here.
Mm, I just remembered actually. There's that old video about we don't know how to compute from Gerald Sussman um,
I think
from
that
that
that's
talk.
the one I watched, but I didn't know propagators at the time.
Yeah, you may want to rewatch that because he actually goes into like some details in how these things work, like internally. Not as deeply as okay, let's see how to actually implement this from the ground up, but he gives you a very good like he gives you a very good sense of okay, yeah, no, if I needed to implement this thing, I know where to begin, you know.
Mm-hmm. Okay. Execution in computation space is a variant of the maximally concurrent model. It avoids the difficulties usually associated with this model. Each constraint is implemented as a thread that executes concurrently with other propagators. Each propagator adds information to the store until no more information can be added. Constraint programming avoids the difficulties of the maximum concurrent model because propagator execution is monotonic. They only add information, they never change or remove information, which is the same plot that we've seen before. That the concurrent declarative model is simpler than concurrent stateful programming precisely because they are also monotonic, which is great. Furthermore, propagators have a logical semantics, so the information they add is consistent with these semantics. If they are written correctly, then the exact order in which they execute does not matter. When they reach a fixed point, man, this is a very nerdy way of saying that, but okay, that's cool. The propagators in the space are no longer runnable. At this point, this function becomes runnable. This procedure implements a distribution strategy. It picks a variable and a value following a heuristic and proposes a guess. For this, it executes. Yeah, this is also opaque. How it creates the guess, who knows?
I would imagine that if you were doing this in Scheme, you would probably use continuations for this.
Sure. For this, it executes the statement choose true, which creates a choice point with two alternatives and blocks until a call to commit unblocks it. The interaction between choose and commit is explained in detail later. The whole computation now looks like this. So somehow the guess box decided that equality and inequality are the guesses. And that's it. The definition of choose is this is the only operation that is called from inside the space, while the other operations are called from outside the space. It creates a choice point with n alternatives. Then it blocks ready for alternative to be chosen by a commit operation on the space. The choose call defines only the number of alternatives. It does not specify what to do for any given one. Choose returns with this binding when alternative this interval is chosen. A maximum of one choice point may exist in a space at any time. Yeah. Yeah, so now we are going to the states of a space. So the space was running concurrently with its parent space. The thread of the search engine now executes this statement, which evaluates to ask. This operation asks the space for its status. In this case, it returns alternatives, meaning that a choice point with two alternatives has been created inside the space. After reduction of the case statement, the whole computation becomes this. Here we give a precise definition of the various states of the space. So it's either runnable or blocked. So runnable is if the descendant contains a runnable thread or blocked otherwise. We run on the threads in the space and its descendants until the space is blocked, while the space can be in one of the following further states. So it can be stable, which means that no additional basic constraints done in the ancestor can make the space runnable. A stable space can be in four further states, like specialization states.
Yep.
Succeeded, distributable, failed, and merged. So succeeded means that it contains no choice points. Distributable means that the space has one thread that is suspended by a choice point with one or more alternatives. A space can have at most one choice point. Attempting to create another gives an error. The space is failed. This means that the state attempted to tell inconsistent basic constraints, for instance, binding the same variable to two different values. No further execution happens in this space. So actually, exceptions are they have a different meaning.
Yeah, if an
They
ex
just stop. They are like space failed.
yeah, if you throw an exception and you don't handle it, and it bubbles up to the top level of the space fails. It's like, yeah, it's different from the other states because you need to be able to tell, okay, this ran, it stopped, it cannot run anymore, but it didn't succeed either.
Yeah. The space is merged. This means that the space has been discarded and its constraint store has been added to a parent. Any further operation of the space is an error. I have a question. So this
Yeah,
means that because you can only have one choice point at a time, right?
yeah.
But uh, are we calling this one choice point and this another one?
No, no, the choice point is the call to choose. This creates a, in this case, you're creating a choice point with two branches.
No, you're right. I it's this is these are branches of the choice point, not different choice points. No, you're right. The space is suspended. This means additional basic constraints on an ancestor can make the space runnable. Being suspended is usually a temporary condition due to to concurrency. It means that some ancestor space has not yet transferred all acquired information to the space required. A space that stays not stable indefinitely usually indicates a programmer error. And ask is essentially a lookup to see the status of a space. As soon as the space becomes stable, A is bound. If S is failed, merged, or succeed, then ask returns those atoms. If S is distributable, then it returns alternatives where N is the number of alternatives. Cloning a space. So the next statement of the search engine thread declares a variable C and creates a copy of the space S. Note that variables and threads belonging to S are copied too, so that both spaces are independent of each other. For the sake of simplicity, we have kept the same identifiers, but they actually denote different variables in the stores. Yeah, so essentially more things.
I'm guessing that the runtime is somehow recursive.
Well, again, if it's close to lexical scoping, as we seen in practice, they probably are implementing this in a recursive manner because they are
What I,
reusing a lot of the operations and things like that.
yeah, what I'm trying to say is that like this sounds a little bit like when you create a space, you were actually creating a nested Mozart VM inside of Mozart.
Oh, it depends if they have a separate abstraction for spaces in the runtime.
Yeah, they might have. Like they may not necessarily implement it this way, but
Yeah, copying a VM sounds
it's
expensive.
well, you do have to copy all the threads and all the variables, right?
Yeah, you have
So
to copy some stuff, but maybe you can not like you don't need some other stuff. Like it really depends on on how worthwhile it is. In the case of what we did in the scoping, we are cloning compilers, but the compiler is not that expensive if you think about it. When we did the entire VM on the first prototype of Carta, copying that would have been expensive.
yeah, because you'd have to copy the entire memory as well, right?
Exactly. Well, but you kind of have to in this case as well, because remember, the bindings they are not bidirectional, which means that only the descendants can see them, which means that you're gonna have to copy anyway.
Yeah, otherwise you would not be able to isolate the bindings so that the parents don't see them, right?
Exactly. So you have well, you can try to make like a workaround of like maybe having some sort of flags, like a flag system. But that sounds
Mhm.
complicated as fuck, man. Like you do an update on a value, but you have to check if the one that is trying to do the lookup has a particular access with a particular flag, And then, oh, you don't have the flag, so you're gonna see the previous value and not the current one, and things like that.
Hmm.
So you can like that would allow you to make the store global, but I would still
That's
not like that idea.
that sounds a little vaguely like a truth management system.
I never heard that term before, but that was just the first idea that came to my mind. If I don't want to copy, if the copy is expensive, then I would, okay, the store is global then, but then I need a system to allow people to see particular versions of bindings.
Yeah, that's I wonder how that would interact with concurrency, right? Because if it's single-threaded, then you can do what we did on the WAM, what the WAM does, right? Where it keeps a trail stack and
Uh
it
huh.
just undoes the bindings.
Uh
Actually,
huh.
whenever it does a binding that's inside of a choice point, it adds it to the trail stack. And if you backtrack, you basically check that stack and you undo any bindings that are there.
Exactly.
Making a concurrent version of that sounds painful, actually.
Yeah, no. When you add concurrency to any idea aside from copying, it becomes a complete hellhole. But well, again, you have to you have to give the attention to the trade-offs, right? So if the copy is like you cannot do it, it's gonna hurt performance to a degree that is not acceptable. Then like they don't have like we have to do it. Like you have to do something about that. Next statement of the search chain thread declares a variable C and creates a copy of space. Blah blah blah. Yeah, I just read that. Yeah, so this is the copy. The definition of clone is a stable. If S is a stable space, creates an identical copy of S and returns a reference to it. This allows both alternatives of the distributed space to be explored. Committing to an alternative. The search engine then executes commit. This indicates to the space S to enter the first alternative. So the call to choose inside the space unblocks and returns 1. The distributed thread then binds X to 4, which leads to the space boom. Yeah, this is very problematic to me, this figure here. Because I don't have the full code and the full context in which these two blocks of code are being used, it's very hard to me to understand in the bigger picture of how this sync process is happening. So somewhere in some code is doing choose, and another piece of code is doing ask. But because I don't really have the context of where they are, it's hard to me to see this like this syncs that and this syncs that. Like
Uh,
where are those? I don't know.
I think we will see an example of that when we get to implementing the relational model in terms of the constraint-based model.
Yeah, sure. Omit if S is distributed spaces causes the choose call in the space to complete and return I as its result. This may cause the space to resume execution. The integer I must satisfy this, where n is the first argument. Yeah, so this is now talking about how they interact. The search strategy and the distributing strategy. The basic technique is to use choose, ask, and commit to communicate between the inside of the space and the search strategy, which is programmed in the parent space. Um, Within the space, calling this first informs the search strategy of the total number of alternatives. Then the search strategy picks one and informs the space. The synchronization condition between the inside of the space and the search strategy is stability. There are no more local deductions possible inside the space. And then finally, merging. The distributed thread terminates because y is determined, so the whole computation becomes this. And so do you have something like this, and it becomes like that, and then well, then we have a bunch of other things. The call to the FES then returns as the letter matches the second clause in the depth first, and the search ends with this statement: the call to merge merges as with the current space. Nothing too surprising. Access by merging. A thread cannot see the variables of a child space unless the child space is merged. Space merging is an explicit program operation. It causes the child space to disappear and all the child's content to be added to the parent space. Yeah, this is the kind of the main difference between this mechanism and scoping, lexicoscoping, because the merge operation is just an implementation detail. The programmer doesn't have access to that. It's not just a normal program operation. Space
Also,
fail.
this merge is destructive, right? It invalidates the child.
No, but the child is kind of like it's a spirit. It is in the parent.
Well, yes, but I do find that interesting.
I wonder what shadowing does to this thing. Because the child may have bindings that are created within the child's space that may conflict with the bindings of the parent. What's the policy then?
I think it doesn't care about the actual names. It only cares about the identities of the data flow variables. I would imagine because that's the actual source of truth in the runtime.
Wait, but do you? I didn't get the part of the question related to the shadowing.
Like if you have a variable a and you use that same variable in a child, then that will get merged. But if you make a local way in the child that shadows the area outside, that's not the same variable, like physically in memory.
Ah, okay,
So they,
okay, I see.
yeah,
Suppose now that the search would continue. This would be the case if the first alternative has no solution. The search engine would then execute the commit. The statement this causes this to return true, which makes the space C evolve to this. As we have seen, the action of the propagators lead to inconsistencies. For instance, this propagates the constraints that the propagator this cannot be satisfied with those values, which makes the space C fail. In a search engine, the call to ask will return failed. This means that C contains no solution. Failures to stateful operations in interaction with the external world are encapsulated in computation spaces in the following way. Exceptions and failures. A thread that tries to add an inconsistent basic constraint to its constraint store will raise a failure exception. What happens then in the top level is implementation dependent. If the exception occurs and the child space is not caught, then the space fails. A failure happening in a propagator immediately results in its space failure because propagators are threads by themselves. Operations on stateful entities across spaces are forbidden, of course. For instance, a thread cannot read or change the value of a cell that belongs to its space parent. A consequence is that only the top level space can interact with the external world. Also, of
yeah.
course.
This point here is actually what makes me think that the implementation of computational spaces is intertwined with the runtime because it needs to be able to intercept any kind of operational cells which are primitive. Um,
Uh huh. Uh huh.
it still would have been interesting to see some of the codes though.
Yeah. I think would be the most interesting part. There is one primitive operation that we have not used, namely inject. This operation is, however, useful because it permits to add constraints to an existing space. For instance, you can constrain the solution of a space to be better than an already known solution. The definition of better is problem dependent, of course. Here's the definition of inject. And this is similar to space creation except that it uses an existing space, it creates a new thread in the space and invokes a procedure in the thread where R is the space root variable. This makes a stable space not stable again. Adding constraints to an existing space is necessary for some distribution strategies such as Brennan bound and saturation. Yeah, but this sounds like you have to have some expertise to know that this is required.
Yeah, this sounds like a low-level primitive.
And a purposeful one, like in the sense that you need to know what you're doing.
Yeah, exactly.
Okay, and now we're going to see the promise that we've seen before on chapter 9 that actually the relational model is implemented in terms of the constraint-based model. So let's see. Choice and fail statements are just some sort of sugar. Not sugar. What's the term they use?
Well, they call it a syntactic abstraction.
Yeah, but we haven't been able to separate, like properly separate those two definitions yet. Okay, cool. The choice statement. This is what we've seen before, and a linguistic abstraction is gonna be to this. This creates a choice point and executes a statement corresponding to the choice made by the search engine. And now the solve function. And then we have this code. Where is the code?
It's on the next page after the exercises.
We
Well,
have
the beginning
this
of the
code.
yeah.
That does.
This code is really interesting. I was looking at this earlier today.
Um, yeah, so this is where the case is happening. The failed succeeded alternatives, and it goes potentially to a loop or a merge. So if it goes to loop, which is a lazy function, I still yeah, I still cannot see the whole thing about what they said before about choose and commit having a synchronization process. The commit is happening here and here, but I don't see how that's. Yeah, I would have to see a full program to have the intuition probably.
Hmm.
But anyway, so this is doing. This is essentially grabbing the I and the N, which are the ones being provided in here.
Ah, it's because you see why we're doing the ask up there.
Yes.
Yeah, that blocks until the space becomes stable, right?
Yes.
And then which alternative we get depends on what happened inside of the space, right? But in particular, the third one, where you get alternatives in, that can only happen if we have a call to choose that's waiting
I
for
also
a
agree with that.
yes, and you would have that inside of the program because you are writing a relational program, so we will have users of choose to say, okay, this can be this or that, basically.
And then you're telling me that this commit before calling solver step unblocks us from the previous call.
Yes, exactly.
Ah, I see. So then you can put this and this in separate threads if you want to.
Uh,
Doesn't
you
seem to be the case,
could,
but it could.
you could, but
Oh no, no, no. This is
that
lazy.
would
So
have,
this is in a separate thread because of how
well,
laziness is implemented in this language.
well, yes, but if you wanted to change the semantics of your relational language, if you put this in a thread, suddenly you have a potentially, well, we probably wouldn't be able to just use a merge in that case, but uh, you would have like concurrent logic programming instead of just
Yeah,
normal
yeah,
logic
yeah.
programming.
It would be like disruptive in comparison to, I don't know, Prolog semantics.
Yeah.
This shows implementation. It is all solution search engine that uses both computation spaces and laziness. The reader should pay attention to where laziness occurs. It is important because of the stateful nature of spaces. For instance, in the else clause of solve loop, a clone of S must be created before any attempt to commit an S. So it's talking about this else here. And why is that?
Remember, commit is destructive.
Ah, the else clone of must be created before. Because of the lazy nature of solve loop, you could actually have declared C and new tail in reverse order. Well, but this is also just abusing the
Laziness. Yeah, this is just abusing laziness. You
not
probably
only
don't want to do it.
laziness, but probably also the nature of like logic variables, because probably if something is unbound, this is gonna block. Yeah, because the value of new tail is not needed before C is committed. But it's more laziness instead of logic variables in this case then.
Yeah.
Okay, and then we have this code that does the thing. Okay, we have the case where I is greater than n, lazily explores the alternatives I through n of spaces S and returns a list of solutions found, appended with solve tail. Yeah, so this means that you're done.
Yep.
This means that you are
This is the last alternative of the
almost
of the
done.
choice. Yeah.
And then this means that you are not done at all and you have to proceed.
Yeah.
And then wait a moment. This is an if else thing and then there's an in here. So you always execute this.
No, this is in the else branch.
Oh, okay, sorry. This is in of the else. Oh, never mind then. You're right. Yeah, these are doing the C and the new tail bindings, and then these is calling the. Well, these are mutually recursive functions, and of course they are tail call because why not?
And lazy, don't forget that.
Well, but laziness seems like an optimization thing there.
um, well, we're using laziness specifically to avoid computing the alternatives that we haven't looked at, right? But yeah, this is more of an optimization of don't do all the solutions that up front, just do them on demand.
It's the same
Um,
thing that we did with the scoping thing.
yeah,
Okay, so language semantics. This is gonna be yeah only 40 minutes, man. We're gonna read. Okay, so the plan is that next time is gonna be the last time of this book. So we're gonna read 13, but we're only gonna probably well, we're gonna skim through it because it's essentially like I'm more interested in the semantics of things, not implementation of them. So if this is more implementation or whatever, we're gonna skim through it. It's 28, 28 pages. There's a lot, those are a lot of pages there. And we also want to
yeah,
combine that with D.
yes, because the these notes here are on language design basically, and I think they are pretty interesting.
Yeah. Yeah, but I think, well, I will have to read all of it. Uh, I will have to read all of it, and I need to do this a little bit earlier because those like 50 pages or something in here. Yeah, pretty much.
All right.
Yeah, this is 37 pages, and this is 28 pages. So that's 60 pages in a single shot.
That's quite a bit.
Yeah. Anyway, I'm gonna finish the recording now.
All right.